We will solve the exercise problems in the ray optics lesson. So we'll go to the first problem. A small candle of 2.5 centimeter in size is placed at 25 centimeter in front of a concave mirror of radius of curvature 36 centimeter. At what distance from the mirror should a screen be placed in order to obtain a sharp image? Describe the nature and size of the image. If the candle is moved closer to the mirror, how would the screen have to be moved? So they've given the size, that is size of the object. The object is candle and the size of it is 2.5 height, and object distance is 27 centimeter. So they are asking us to find what is the image distance. So at what place we have to keep the screen so that we can obtain a sharp image, and then we have to find what is the nature and size of the image. And suppose if the image is screen is going to be moved closer to the mirror, so where we have to move the screen, that also we have to find. So they have given it as a concave mirror, so we have to use the mirror formula. So here our object is, so the given is, first we'll see the given. So the object size is height of the object is h, that is 2.5 centimeter, and image height we need to find, so that one we'll keep it as h dash. Object distance, it is 27 centimeter, and here as it is a concave mirror, using sign conventions, for a concave mirror it is negative, so minus 27 centimeter. Then they have given the radius of curvature of the concave mirror, so that's also minus 36 centimeter. So if we want to find the focal length, already we have seen, we'll use the formula relationship between focal length and radius of curvature. It's nothing but half of radius of curvature will give the focal length, which is nothing but minus 18 centimeter. And we need to find what is the image distance. So image distance, we are going to use the mirror formula. So mirror formula, we know it is 1 by f is equal to 1 by v plus 1 by u. So from this we can find what is the image distance. So 1 by v will be equal to 1 by f minus 1 by u. So I have substituted the values of the focal length. So focal length is half of the radius. Minus 36 divided by 2 will give us minus 18. And then object distance, it is minus 27 centimeter. So when we take LCM, we can find what is the image. So the image distance is 54, minus 54 centimeter. So only at this point, if you're going to place the screen, we can get a sharp image. Now the next one, they have asked the nature and size of the image also. So for this we have to use the magnification of the mirror. So again, magnification formula, we know it is m is equal to h dash by h is equal to minus v by u. So image distance also we have found, object distance also it's given, h, that is object's height also it's given, we need to find h dash. So just cross multiplying this h to the right hand side, we'll get h dash is equal to minus v by u into h. So when you substitute the values, for v it is minus 54 and u is minus 27, and h height of the object already it's given in the question, it is 2.5. So when you solve it, we will give the height of the candle's image which is obtained on the screen, that is 5 centimeter. And negative sign, as it is a concave mirror, for a concave mirror we'll get a real and inverted image. So if we are going to move the mirror close to if the candle is moved very close to the mirror, then what we have to do is we have to move the screen away from the mirror. That's it. Then the second one, it's also again about convex mirror. So a 4.5 centimeter needle is placed 12 centimeter. So 4.5 centimeter needle. So it says that is the height of the needle. And where we are placing, it is being placed away from a convex mirror. So that is the object distance, that is 12 centimeter. And it is having a focal length of 15 centimeter. Give the location of the image and magnification. Describe what happens as the needle is moved farther from the mirror. So it's again similar to the first one. So height of the image, it's 4.5 centimeter. Object distance, again it's minus 12 centimeter. For convex mirror, using your Cartesian signs, only for object distance it will be negative. Your image distance and focal length will be positive. So here focal length they have given it directly, it is 15 centimeter. Image distance we need to find, and the magnification also. So again the same formula, mirror formula, that is 1 by f is equal to 1 by u plus v. So 1 by v will be equal to 1 by f minus 1. Now we'll substitute the values of the object distance and focal length. So when you substitute the values for the image distance and object distance, 15 centimeter and 12 centimeter, and if we take LCM, we will get the image distance is 6.7 centimeter. For finding the magnification, we will use the magnification for a mirror, that is m is equal to h dash by h is equal to minus v by u. So h dash, either you can write as h dash by h, that is the ratio of the image height of the image to the object, height of the object. So when we substitute the values of the image distance, object distance, and the height of the object, which we have found, and the height of the object is given already in the question. So image distance is minus 6.7, object distance is 12, and height of the object is 4.5. So when we solve it, when we calculate it, we'll get the magnification, we'll get the height of the image as 2.5 centimeter. Now if we substitute it in the magnification formula, we can find whether it has got magnified or it is reduced, or whether the image has got reduced in size. So we know m is equal to h2 by h1 is equal to 2.5. What we have found, height of the image to the height of the object. 2.5 by 4.5. When we divide it, we will get 0.56. So the height of the image is 2.5 centimeter, and positive sign is going to indicate that the image is erect, virtual, and diminished. Now we'll move on to the next one. A tank is filled with water to a height of 12.5 centimeter. The apparent depth of the needle lying at the bottom of the tank is measured by a microscope to be 9.4 centimeter. What is the refractive index of the water? So apparent depth is, so if we are going to see through the tank, we will be viewing that as if the needle is lying a little bit above, but that is not going to be the original position. So that's the reason they have kept it as apparent depth, and we need to find what is the refractive index of the water. Then mu we have to find. If water is replaced by a liquid of refractive index 1.63, so we are using another liquid, we are replacing the water by another liquid which is having a refractive index mu of, or n of 1.63 up to the same height. By what distance would the microscope would have to be moved to focus on the needle again? So again, due to refraction, what will happen? The needle's position would change because we have replaced the water by some other liquid. So now we have to find what is the distance of the image now. So actual depth of the water, that is height, is 12.5 centimeter. But when we see through it, the height is of the needle in the water is 9.4 centimeter. Then we have to find what is the refractive index. So here refractive index, we can find the speed of, generally refractive index is nothing but the ratio of speed of light in medium divided by the ratio of speed of light in vacuum. So here it's going to be the same thing. So height in water, that is apparent actual height divided by the apparent height of the needle. So when you substitute the values, we will get 112.5 divided by 9.4 will give us 1.33. Now what will happen is, so the actual depth of the needle remains same, but its apparent depth will be changing. Why? Because we are replacing the water by another liquid which is having a refractive index of 1.63. So when we replace it, we need to find what is H2 here. So H1 is going to be the same one. So we can keep this as refractive index of the liquid is mu dash, which is equal to H1 by Y. So what is the apparent position we need to find? That is H2. So here we know what is mu dash, and H1 we know that is the same height, the water level, how much we have filled. Till that same level we will be filling it with another liquid. So when you substitute the values, it is going to be 12.5 divided by refractive index of the liquid is 1.63. So when we divide it, we will get what is the apparent depth. Now here the new apparent depth due to the other liquid is 7.67 centimeter. So which is less than the apparent height of the needle when it is placed in water. So here that is 9.4. So here at what distance they are asking at what distance we have to move the microscope. So if we take the difference between these two values, then we can find at what distance the microscope is have been moved. So 9.4 minus 7.67 will give us 1.73 centimeter. So the distance of the microscope should be moved to 1.73 centimeter. And then the next one, now we have two figures here. Figure 9.34a and b show refraction of a ray in air incident at 60 degree with a normal to a glass air and water air interface respectively. That is, for two different mediums, they have given the angle of incidence. Then predict the angle of refraction in glass when the angle of incidence in water is 45 degree with normal to water glass interface. So first we are having two interface, that is glass and air, air and water. The last one is glass and water. So we need to find the refractive index for glass and water. So this is nothing but total internal reflection, and we can use the Snell's law formula also, that is mu is equal to sin I by sin R. So we know mu is equal, this is Snell's law, that is law according to laws of refraction, we know mu is equal to sin I by sin R. So first we'll take the first figure. So in the first figure, the two mediums are glass and air. So the angle of incidence is 60 degree and angle of refraction is 35 degree. So we can find what is the refractive index of glass with respect to air. So when we substitute sin 60 and sin 35 degree value, we will get the refractive index of glass with respect to air is 1.51. Similarly, the next one, if we see, we have air and water. So if you see the ray diagram, what happens? Light is entering to air and then leaving through water. So what happens there? The angle of incidence is 60 degree and the angle of refraction is 47 degree. So you have to look at the arrow marks also in the three ray diagrams. So angle of incidence is 60 and angle of refraction is 47. So again the same Snell's law formula, mu is equal to sin I by sin R. If we substitute the values of sin 60 and sin 47, we will get the refractive index for air to water interface. Now what happened is, we have found the refractive index of glass with respect to air, and we have found the refractive index of air with water interface also. So now they have asked us to find glass and water interface. So we are just going to divide both the values what we have got with respect to glass and water and air. So we can guess what is the refractive index of water and glass. So if we substitute the values, we'll get 1.51 divided by 1.84 is equal to 1.275. But they have asked what is the angle of refraction also. So if you see in this diagram what happens, light is entering through the water surface and refraction is taking place at the glass surface. So here the angle of incidence is I is 45 degree. According to Snell's law, we know mu is equal to sin I by sin R. So I value is 45 degree and refractive index we have already found it is 1.275. So when we substitute the values and values we'll get sin 45 value is 1.275, sorry, root 2. So we need to find sin r here. So we have to take the reciprocal of it. So we'll have it as 1 by root 2 into 1.275, which is nothing but 0.55. Again we have to find only r. So we have to take sin inverse of 0.5. So it is approximately it's going to be near to 30s only. So you can use the logbook and we can find what is the value of sin inverse of 0.5546. The next one, double convex lenses are to be manufactured from a glass of refractive index 1.55. So refractive index of glass is 1.55 with both surfaces of same radius of curvature. That is a convex lens. A normal convex lens is also called as double convex lens. What is the radius of curvature required if the focal length is to be 20 centimeter? So we have to find what should be the radius of curvature if the focal length is to be 20 centimeter for this lens. So we have to find R1 and R2 here. Because it is a convex lens which has two radius of curvature. Lens will have two radius of curvature. Refractive index of glass is 1.55. Focal length of the double convex lens is 20 centimeter. And on both the surfaces, the radius of curvature on both the faces is kept as R1 and R2. So radius of curvature for convex lens, R1 will be plus R and R2 will be minus R because it's same. Both the faces are going to have same radius of curvature. So now we are going to use the lens maker's formula. So according to lens maker's formula, we know 1 by f is equal to mu minus 1 into 1 by R1 minus 1 by R2. So already the value of refractive index of glass is given, focal length is also given, that is f is 20. So when you substitute the values, instead of R1 and R2, we'll substitute Rn minus R. So minus will become plus here. So 1 by 20 will be equal to 0.55 into 2 by R. So when we solve this, we'll get the radius of curvature of the lens will be 22 centimeter. We'll move on to the next one. A beam of light converges at a point P. Now a lens is placed in the path of a convergent beam 12 centimeter from P. At what point does the beam converge if the lens is a convex lens of focal length 20 centimeter and a convex lens of focal length 15 centimeter? So we have to find what is the image distance in case of a convex lens and concave lens. So we are going to use a lens formula only. So that is 1 by f is equal to 1 by v minus 1 by u. So for a convex lens, if the focal length is 20 centimeter, the object distance is 12 centimeter for both concave and convex lens. So here, as it is convex lens, it will be taken as positive. So when we substitute the values of u and f, we can find the image distance. So for convex lens, when we take the LCM, we'll get a 7.5 centimeter. Then focal length of concave lens is, they have given it as 16 centimeter. According to Cartesian signs, we know it is minus. So focal length will be taken as minus 16 centimeter. Object distance is the same, only 12 centimeter. As it is a concave lens, it will be taken as negative. We'll use formula, that is 1 by f is equal to 1 by v minus 1 by u. So from this we can find what is 1 by v. So 1 by v will be equal to minus 16 plus 1 by 12. Minus and minus will become plus. When we take LCM, we'll get the image distance is 48 centimeter. Then question number 7. An object of size 3 centimeter is placed 14 centimeter in front of a concave lens of focal length 21 centimeter. So they have given an object size. So H1 is 3 centimeter and placed in 14 centimeter in front of a concave lens. It is understood that it is the object distance and focal length is 21 centimeter. So we have to find what is the image produced by the lens and what will happen if we are going to move it away from the lens. So height of the object they have given, object distance, focal length of the lens. So concave, it's a concave lens. So object distance and focal length both are negative. So as it is a lens, we will use lens formula. So we know lens formula is 1 by f is equal to 1 by v minus 1 by u. From again we can find 1 by u from this. So 1 by v will be equal to minus 1 by 21 minus 1 by 14. So the image distance is minus 8.4 centimeter. So negative sign says the image is erect and virtual. So we have to find, they have asked us describe the image produced by the lens. So we have to find what is the height of the image and magnification also. So magnification of lens is nothing but again H2 by H1 equal to V by U, because it's a lens. For mirror only it will be taken as minus V by U. So H2 by H1 is equal to V by U. H1 already they have given, image distance, object distance also we have found. So when we substitute the values, we'll get image distance is minus 8.4, image distance is minus 8.4, object distance is minus 14 and height of the object is 3. So when you substitute the values, we'll get it as 1.8 centimeter. So that is the height of the image. So suppose if we are moving the object further away from the lens, what will happen is again the virtual image will also move towards the lens but not beyond the focus of it. So the size of the image will decrease as the object distance is going to increase. Then the last one. So what is the focal length of a convex lens of focal length 30 centimeter in contact with a concave lens of focal length 20 centimeter? Is the system a converging or a diverging lens? So here two lenses are joined together. So this is nothing but combination of lenses. So first convex lens will keep it as f1. Concave lens will keep it as f2. We have to find the total focal length. So 1 by f will be equal to 1 by f1 plus f2. We just need to consider the Cartesian signs. For concave lens, it is negative. The focal length is negative. So 1 by f is equal to 1 by f1 plus 1 by f2. So 1 by f will be equal to 1 by 30 minus 1 by 20. Minus 1 by 20. So when we take LCM, the focal length will be minus 60 centimeter. So the focal length of combination in case of convex and concave lens is 60 centimeter. Negative sign, it is going to indicate that it is a diverging